Hey guys, welcome. Yeah, so this is an exciting video because by the end of this video, we're going to be able to find an explicit formula both for the Fibonacci number sequence and the Lucas number sequence. Yeah? Okay, now, before making this video, I already made 4 videos on solving recurrence relations, and each of them is interesting and useful, so you should watch all 4 of them in order. But at minimum, you should watch the last video I made, which is example 1, where we learned how to solve recurrence relations of degree 2, where the characteristic equation has distinct roots, because such is the case here. This here is a recurrence relation of degree 2, and we'll see shortly that the characteristic equation to this recurrence relation has 2 distinct roots. And by the way, you should reckon that this recurrence relation defines the Fibonacci number sequence. Additionally, the same recurrence relation defines the Lucas number sequence. That's to say that the only difference between the Fibonacci and Lucas number sequences is how they start. Yeah? Okay, cool. Now, to begin solving, we get everything on one side and 0 on the other side. And then from there, we gather that the characteristic equation in this particular case has to be this. If you don't see why, then watch example 0 or the video on the general approach. Yeah? Okay, all right. Now, from here, from the characteristic equation, we solve and see that r can take on 2 values. And therefore, the characteristic equation in this case has 2 distinct values or roots. Yeah? Okay. And the 2 roots to our characteristic equation are this here and this here. Yeah? Okay. Now, in the video on the general approach, we said that if you have a recurrence relation that's degree 2 with 2 distinct roots, then we know that the solution is given by this here, right? So again, watch the video on the general approach. But yeah, we said there that if you have a recurrence relation of degree 2 like this, then the solution will look like this, right? Okay, cool. So let's jot this down because we need the space. So let's write it up top. And notice that this particular recurrence relation is the Fibonacci number sequence relation, and it's the same as the Lucas number sequence relation. So more generally, we can write it like this if the F makes it biased towards the Fibonacci. And we'll get an alpha Lucas in a little bit. Yeah, but yeah. Okay, so now that we have that, let's make space and see that based on this claim here, a claim made and proven in the general approach video, we see that the Fibonacci recurrence relation, this here, right, will have a solution that looks like this, where we have alpha, right, and then r1 to the n plus beta r2 to the n, where r1 and r2 are the 2 roots of our quadratic characteristic equation. All right. Where to from here? Well, the only thing left to do, and therefore the distinction between the Fibonacci number sequence and the Lucas number sequence, is the value of alpha and beta. So for the Fibonacci number sequence, we know that it starts with 0 and 1. So we can let a0 be equal to 0 and a1 be 1. So we get some initial conditions. That way we can solve for alpha and beta. And for the Lucas numbers, like we said, the only difference is the start, the difference between the Fibonacci numbers and the Lucas numbers. And so a0 for the Lucas numbers is 2 and a1 is 1. Yeah? Okay. So with this, let's recall our 2 roots, or you could rewind. To get an explicit formula for the Fibonacci numbers, like I said, we just have to solve for alpha and beta using the initial conditions. And so one of the initial conditions was a0 is equal to 0. And from that, we see that we get alpha times r1 to the 0 plus beta times r2 to the 0. And r1 to the 0 and r2 to the 0 are just 0. So from there, we get 0 equals alpha plus beta, which means alpha is the additive inverse of beta. Yeah, okay. And then using the other initial condition, we write this here, right? And I guess I could clean it up by getting rid of the ones there and the bridge there. And so if we do that, then we get this. And we get this actually together from this equation and this equation. from this first equation on alpha and beta, we saw that alpha is equal to negative beta. And then we have this equation. And so here, instead of beta, we can put negative alpha. If alpha is negative beta, clearly beta is negative alpha. So instead of beta here, I've put a negative alpha. Yeah? Okay. And then to solve for alpha, I did this. What did I do? Well, I factored out the alpha because both this guy and this guy have an alpha. And then I distributed this minus sign to here so that I have root 5 minus 1 instead of 1 minus root 5. Yeah? Okay, I didn't just get rid of the negative that was there. Okay. And so now if you combine these guys, you get 1 plus root 5 minus 1. The ones cancel, so you get 2 root 5 over 2, which is just root 5. So you get 1 equals alpha times root 5. So 1 equals alpha times root 5, meaning alpha is 1 over root 5, and therefore beta is negative 1 over root 5. And so that brings us to the conclusion for the Fibonacci number sequence, which is that the explicit formula for the nth number in the Fibonacci sequence is this right-hand side. Isn't that cool? All right. So you can imagine that the Lucas number sequence is also going to have a very similar formula to the Fibonacci number sequence, right? Being that the recurrence relation that defines them is the same. But yeah, obviously we have to solve for a different set of alpha and beta, right? Okay, so again, recall that the Lucas number sequence is defined by the same recurrence relation as the Fibonacci number sequence. So here I just changed the F's to L's, right? But the start is different, right? Okay, and so you get it. To find an explicit formula for the Lucas numbers, we use the two initial conditions. One is A0 being 2, and then the other is A1 being 1, and that's this. From A0 being 2, the equation that we get to solve for alpha and beta reduces to this, which in turn reduces to this, which is same as that, right? Okay. And then from the initial condition that L1 is 1, we get this equation. And then now we could substitute for beta with 2 minus alpha in our next step. And if we do that, we get this. And then it's just arithmetic or algebra. Yeah, you could negotiate that on your own. But from this equation, it's easy to see that you could get to this equation, right? And then remember, inside of here, when we solved for the Fibonacci number sequence, these two guys, which were identical to earlier, except for this extra part now, right? These two guys combine to 2 root 5 over 2, which was just root 5. So you'll have a times root 5 here, right? And then plus 1 minus root 5 here. Well, the ones are going to cancel. And this minus root 5 we can throw on the left side to reduce this whole equation to this, meaning alpha is equal to 1 and therefore beta is equal to 1, since alpha plus beta is equal to 2. So that means that the Lucas number sequence will have a much cleaner formula, right? And, well, a cleaner formula, which is this. Yeah? All right, cool. I hope you enjoyed this, and keep watching. There will be at least, what is this, example 2? At least 3 more examples on solving recurrence relations, and they'll get progressively more challenging. And the next example, example 3, we'll look at the repeated root case for recurrence relations of degree 2. Yeah? Okay, all right. Take care.